Your first podcast. Let's see how it goes, girls. As you can see by this slide, I've got two goals to accomplish this morning in this podcast. And so let's start with the qualitative aspect of acids and bases and then proceed into the quantitative. So by review, definitions of Arrhenius's, Bronsted-Lowry, and then Lewis acids and bases. Remember that the broadest definition goes to Lewis's acid and base definition, an electron pair donor and acceptor for both bases and acids. Think about when you're looking at and comparing these three definitions, how they don't contradict one another, but they expand upon the definition. If you think about, for example, Bronsted-Lowry is a proton donor. A proton is a hydrogen ion when we look at it more closely. And so does a proton have any electrons at all? And the answer is no. And so that's why Lewis would define it as having the ability to accept a pair of electrons. So a proton donor and an electron pair acceptor go hand in hand. Likewise, a proton acceptor and electron pair donor also go hand in hand. So there's no conflict there. And again, if you look at the Venn diagram that I drew before, you can see that I'm trying to give you a feel for which is the most inclusive definition of acids and bases. So let's address this question head on by an example that relates to your lab. If you look at this equation, your equilibrium lab, we have an iron ion, we have SCN, the thiocyanate ion, and the complex ion that is formed, the red colored solution. So if you think about the definitions of proton, donor, and acceptor and producing hydrogen ions in solution, you might look at this with a big question mark in your head and say, well, absolutely not. Lewis would be the only possible acid-base definition based on what information you see here, and you're absolutely right. The iron ions and the SCN. Now, in order to address this question, you're going to have to look at the structure of FeSCN in order to understand it more carefully. So let's zip over to that one and just focus your attention on, there we go, on this equation. If you look at it, you see the iron ions, and I drew the Lewis structure. You might call attention to the fact that Lewis structure, Lewis acids and bases, I believe it's the same Lewis. Anyway, with this Lewis structure, you see that the thiocyanate ion does have a number of lone pairs on the ion that can serve as electron pair donors. Okay, and so the iron ion, it has lost its valence electrons, and so it serves as the electron pair acceptor. The interesting thing about some of these Lewis acids and bases, at least those that fall outside of the Bronsted-Lowry group, you have an acid and a base, the iron and the SCN, but you only have one product. You don't have the conjugate pairs in that type of acid-base definition like you would for Bronsted-Lowry. So that's an interesting thing to think about. A second example of Lewis acid and base might be, if you look at another practical example, is that this solution, the aluminum nitrate solution, is actually an acidic solution. And if you remember, the nitrate ion is not an ion that is acidic. It's a neutral ion. But the aluminum ion is said to be acidic. Well, why is that? Well, it has to do with Lewis acids and bases. The aluminum ion has to act as an electron pair acceptor from the water. Okay? And in doing so, the aluminum ion has lost its valence electrons, whereas water has on its oxygen, 2 pairs of electrons. And these 2 pairs of electrons can be donated to the aluminum ion. And it turns out that for aluminum ion, 6 water molecules can bond with the aluminum to form this sort of complex ion. Now, a couple things to notice when you look at this complex ion. Number one, this is what's called, each of these bonds to the aluminum is an oxygen-aluminum bond. And in each case, the water supplies the electrons that are bonded to aluminum. Oftentimes with this kind of complex ion, what you have is the number of water molecules, and the water molecules in this case, the water molecules are actually called ligands. Perhaps you remember this term from biology, but a ligand is part of the idea behind hemoglobin, chlorophyll, and so forth, where inside the middle of the structure you have a metal ion. Same thing goes here. The water molecule supplies the electrons. The aluminum ion is kind of sandwiched inside. In hemoglobin, it's an iron ion that's sandwiched inside. And these ligands are actually good examples of Lewis acids and bases, and oftentimes transition metal ions as well as aluminum ions serve as Lewis acids, electron pair acceptors. So you have another thing, we'll come back to this later, but it turns out that if the charge is +3, and we'll learn again, this is like a chapter 22 thing that we'll learn more details about, but the aluminum +3 ion, you notice that there are 6 waters around it. More as to why that's the case later on in the year. So what makes this acidic? It just looks like there's 6 water molecules surrounding the aluminum. Well, it turns out in water, because of the strength or weakness, if you want to call it, of all of these bonds, that a ionization occurs. One of the hydrogen breaks off, as you can see here by the broken bond link, and combines with the water to produce hydronium ions. That's what makes the presence of hydronium ions greater than hydronium ions greater than hydroxide ions makes the solution acidic. Okay. Now, actually, this setup here, this equation, does look like Bronsted-Lowry, as well as falling into the Lewis structure. Electron pair donor to the hydrogen ion, as well as proton donor to the water. So Lewis acid and Bronsted-Lowry acid on this complex ion. And then in this case, we have the water is serving as the base, both the Bronsted-Lowry and the Lewis acid. Again, you have to be kind of attentive to the detail of the charges of ion to get this figured out, but practice this a bit more and I think it'll become a little bit easier to understand. Okay, so final question. What about this one? If you look at this equation, and I guess I should have drawn a second arrow here. If you look at this equation, according to whom would ammonia be considered an acid or a base? Ammonia in water, does it produce hydroxide ions? Yes. So what would you say? It's an Arrhenius acid, Arrhenius base. You're right. And does the ammonia accept a proton from water? Yes. So not only is it an Arrhenius base, but it's also a Bronsted-Lowry base. And then finally, Does the ammonia donate a pair of electrons to water? Yes. So ammonia would be considered a Lewis base. So this is an example that falls inside the entire Venn diagram here, something that is a Lewis, Bronsted-Lowry, and Arrhenius base.